we talk about the Bohr atomic model. In our previous video, we have talked about different atomic model, which include Thomson atomic model, which is Plum-Ponney model, Rutherford nuclear model of an atom. We have also talked about the Millikan oil drop experiment, discovery of nucleus, discovery of electron, calculation of charge per mass of an electron. And the last one that we talked about was Rutherford model of an atom, where we mentioned that an atom consists of an atom contains a massive and a positive center called the nucleus, something like this, called the nucleus, and it has an electron that is revolving around it, just like the planet revolve around the sun. And that is what we have for um, Rutherford atomic model, which is the nuclear model of an atom. And in Saget-Thomson atomic model, we say an atom is a small sphere with a positively charged and negatively charged embedded in it. We have already mentioned these models before. But Bohr atomic model is an advancement to to Thomson and Rutherford atomic model, and this model was proposed in the year 1915, and it comes with the modification of Rutherford's atomic model. Like I say, Rutherford atomic model says an atom has a large center, a large and heavy center, which is the nucleus, and has an electron that's revolving around it. And it also says that the weight of the nucleus, the weight of the atom is concentrated in the nucleus, and the volume is concentrated in the what? In the electron. Now, the Bohr atomic model says an atom consists of a small nucleus, which is positively charged, and it is surrounded by electron moving around the nucleus in an orbit, not like a planet. This one is called the planetary model of an atom. Planetary model of an atom. But this one says it moves in a particular orbit, something like this. We have a positively charged center, and we have electron that moves around it in a orbit, something like this. That is what Bohr atomic model is saying. But what is the postulate of Bohr's atomic model? The postulate of Bohr atomic model is what you are seeing on the screen right now. And I'll be explaining with a particular image so that you can understand and you can visualize what the Bohr atomic model is all about. Now, this is what I'll be explaining with based on the energy level. It says in an atom, electrons which are negatively charged revolve around the positively charged in a definite circular path called orbit or shells. And each orbit acts a fixed energy, and this circular path is known as orbital shells. So we have orbits like this. These are orbits. This one that label 1, 2, 3, 4. Each of these orbits has their own energy level, and this circular path is called the what? Is called the orbit. So in each orbit, we have an electron that revolve around the what? That revolve around the nucleus. And each orbit has their own name. We give them the name, and we'll be talking about the quantum number very soon. We give them the name. The first orbit is given K. The second orbit is given L. The third orbit is given M. And the fourth one is given N. Now, we now say electrons revolve around the nucleus. We have a center which is positively charged, and we have electron revolving around the what? Electron revolving around the nucleus, right? So we have a positively charged center with an electron revolving around it in a circular path. Now say the energy level represents by an integer, like I've shown before, which is integer 1, 2, and 3. And each of these integer is known as quantum numbers. Like I said, we'll talk about the 4 quantum numbers that we are having. And the range of quantum numbers start from the nucleus, which we start from the nucleus side where n equals to 1. So let me just clean this so that you can visualize it well. So can you see this is the nucleus here? This one you see, this is the nucleus here. And you see that at the side of the nucleus, we have the what? We have the first orbital, right? So it says that each energy level is represented by the what? Is represented by n equals to 1, having the lowest energy level. which means energy level increases from this place to this place. Are you getting me now? It increases. This is the one with the lowest energy level, and this is one with the highest energy level in this case. Are you getting me? Now, the electron in an atom move from lower energy level to higher energy level, and this lower energy level is termed the ground states. This lower energy level is termed the what? Is termed the ground states, and the higher energy level is termed the excited states. And the move from ground state to excited state by what we know as quantum or photon jump. And we have how to calculate the change in energy from ground state to excited state. We have change in E equals to higher energy in higher energy level minus energy in lower energy level, which is equals to HF. Our H is the Planck constant. H is Planck constant, and F is our frequency of the photon. Now, it also states that the angular momentum MVR of an electron is equals to the integral multiple of Planck constant divided by 2 pi. So our N is our energy level, where we have N can be equals to 1, 2, or 3. Our M is the mass of electron. Our V, mass of E. Our V is the velocity of electron. Which one again? Our R is radius of the orbits that we're studying, radius. H is Planck constant, like I've mentioned here, which means from this statement we say that what? We say that angular momentum of an electron orbiting around the nucleus is the integral multiple of Planck constant divided by 2 pi. Right? Now, that is what we have for Bohr atomic model. We now have how to calculate atomic radius. We have how to calculate atomic radius using combination of Coulomb's law and this thing. So we have something like this. We have our center, which is the nucleus. Now, there will be, if there is an electron here, for example, remember that an electron is what? An electron is negatively charged, right? Since an electron is negatively charged, and we all know that like charges does what? Like charges attract, right? If you have like charges repel rather. Like charges repel. If you have a positive and a positive charge, they are going to repel according to physics. They are going to repel. But if you have a positive and negative charge, they are going to attract. So like charges repel and unlike charges does what? Unlike charges attract, right? Like charges repel, unlike charges attract. So there will be a force of attraction between the nucleus and the electron that is here. There will be a force of attraction. Also, this electron is moving at a particular velocity around the nucleus. It is moving at a particular velocity around the nucleus. Now, this thing moves with a centripetal force because it is moving in a circular path. And we know that centripetal force, which is F, equals to what? Equals to mv squared upon r. So using centripetal force and the combination of Coulomb's law, where it says F equals to z e squared over r squared, right? Which is Coulomb's law. If you combine these two laws, and we can use it to derive a particular equation that says that calculates the radius of electron, and says r equals to n squared h squared divided by 4 pi squared me squared, and n is the what? N is the quantum number, like the energy level rather. N is the energy level, H is Planck constant, M is mass of electron, and E is charge of electron, right? Now, apart from that, we now also have something called atomic spectrum of hydrogen. You see, In the year 1884, J.J. Balmer observed that there were four prominent color lines in the visible hydrogen spectrum, and that is red line, blue green line, blue line, and violet line. But let me quickly show you what this atomic spectrum is all about. We have them here. Can you see? This is what we have here. So this is atomic spectrum of hydrogen. But before we go into this, the series we in this blue green line red line we have some series, right? And we have what we known as we have the Lyman series, Balmer series, Paschen series, Brackett series, and Pfund series. Also, we have Humphrey. Now, in this, we have something we call Balmer's equation. And this Balmer's equation will be using a constant known as Rydberg constant. And that equation is 1 over lambda equals to the Rydberg constant into bracket 1 over n1 squared minus 1 over n2 squared. We'll be talking about the application of this particular equation later. But what do we have here? We have the ground state. Remember I told you that n equals to 1 is the ground state, and we have the excited state, which is the what? Which is the ones that are here. Now we have the Lyman series, and you can see the color that the energy range that it is at ultraviolet, right? This one is at near infrared, this one is far infrared, and this one is also far infrared. And we should note that we have, from the image that I show here now, we have how many spectral series. We have 1, 2, 3, 4, 5. We have 5 spectral series, though there's still one more, which is Humphrey, but we are not talking about that one yet. Now, apart from Bohr's atomic model, I said we have something called the quantum number. What is the quantum number? You see, from the Schrodinger wave equation that I mentioned in one of our past videos, we have four quantum numbers. And what are the four quantum numbers that we have? We have the principal quantum number, We have the quantum number, azimuthal, quantum number. We have the magnetic quantum number, magnetic, and we have the spin quantum number. So the principal quantum number is denoted with n. So if you see n, that is principal quantum number. The azimuthal quantum number is denoted with L, the magnetic quantum number with M, and the spin quantum number with S. So we have them like this. So this principal quantum number, what does it determine? It describes the size of an orbital and also the energy level of an orbital. And we have a particular equation, which is 2n raised to power 2, where our n is the energy level of an electron. For example, like I mentioned, we have let me say n orbital and maximum number of electrons that they can have in each orbital. So we have 1, 2, 3, 4, for example now. Then what are the orbital? The number one orbital is k, like we have mentioned before, L, M, N, right? So since we are using 2 raised to power 2, n raised to power 2, that is n equals to 1, that is equals to 2, 1 raised to power 2, and that's equals to 2. So in K shell, in K orbital, or the K shell rather, I mean shell, this should be shell. In K shell, we have 2 maximum number of electrons. In L shell, we have 8, because 2, that is 2 into bracket 2 raised to power 2. Then we have 2 into bracket what? 2 raised to power 3. That's equals to 2 times 8. That is 16. And we also have 2 into bracket 2 raised to power 4. And that's 32. That is the maximum number of electrons that it can occupy, right? So it is just like the one that we have here. We have a nucleus, right? We have a shell, we have a shell, we have a shell, we have a shell. And the one that is inside is known as what? The K shell, right? We have the L shell, we have the M shell, and we have the N shell, right? So for this K shell, the maximum number of electrons that it can occupy is 2. For this L shell, the maximum number of electrons that it can occupy is 8. For this M is 16, and for this N is 32, right? Sorry, this one should be 18 instead. I think I made mistake with the calculation. 18. Pardon me. Let me see where I made mistake. This is supposed to be 2 raised, but that's sorry. I've seen where I made mistake. So we have supposed to be 2 into brackets 3 raised to power 2, and that's 2 times 9, that is 18. And this one is supposed to be 2 into bracket 4 raised to power 2, and that's 32. So that is what we have here. 2, 18, 2, 8, 18, 32, right? And azimuthal quantum number, where do I write it? So I said principal quantum number determine the what? Determine the size. So I'll be writing what they determine in front of them. Determine the size. Azimuthal quantum number describes the shape of an orbital. Describe the shape of an orbital. What does magnetic quantum number describe? Magnetic quantum number describe the orientation or distribution of electron cloud. So describe the orientation or distribution of electron cloud. And spin quantum number describe the state of an electron. State of an electron. So for the shape of an orbital, we have 4 orbitals. What are the 4 orbitals that we have? Orbitals. We have the S, P, D, F, which is spin, principal, diffuse, and fundamental. So for the S, we have a spherical shape. For the P, we have the dumbbell. For the D, we have the double dumbbell, where we can have something like this, right? We can have something like this. And for the F, we have rosette or complex. So for this P, we can have PX, we can have PY, we can have PZ. For this D, we can have the XY, the ZY, and other stuff like that. We have something like this. We can have something like this. So it is double dumbbell. This is dumbbell shaped, and this is double dumbbell shape. So this one is saying the what? The shape of an orbital. And this one is talking about the orientation of an orbital, because we have orientation. Now, which law states the orientation of an orbital? We also have some other rules in, apart from Bohr atomic model, we also have other rules like Pauli exclusion principle, Alval principle, and Hund's rule. And these all these rules that I just mentioned now, let me write it down. We have Pauli exclusion principle, Alval principle, and untrue. What do they state? Untrue. You see, Pauli exclusion principle states that no electron in an atom have the same set of 4 identical quantum numbers. Have the same set of 4 identical, which means if they have the same size, they have the same shape, they have the same orientation, they cannot have the same spin. I get me now. They cannot have the same spin. For example, now this is an orbital. This is how an orbital looks like. Let me show you. This is how an orbital looks like. This is an orbital. So this is Pauli exclusion principle. You will see that this thing, we have something like this. This one goes up, it spin upward, and this one spin downward, right? But this one spin upward and upward, which is not possible. It is not possible for both of them to have the same spin. But this one is correct because we have one upward and we have one downward. And this one as well, we have 1 upon 1 down. That's why it's correct. That is Pauli exclusion principle. What about untrue? For untrue, it says that in arrangement of electron inside an orbital, you have to arrange singly before forming any pairs. You have to arrange singly before forming any pairs. You see that for this one, they arrange everything singly first, and it is marked in an orange color. Everything singly, right? Then 2 are left, then we start pairing. But it is wrong for you to start pairing before arranging singly. It is wrong for you to have a particular, when there is an electron left, you're now having an empty orbital that is here. So you have to arrange singly first before you pair. Now, what about the Aufbau rule? And this is known as building up principle. And it says that in filling electron in an atom, the lower energy level must be filled first before the one with the higher energy level. So if you notice very well, n equals to 1, we have to fill the n equals to 1 first before moving to n equals to 2. So you fill the one with the lower energy level first before filling the one with the higher energy level. Now the question is, how do we fill orbital? How do we arrange electronic configuration? Now, I've already mentioned the concept of SPDF. I did not mention the maximum number of electrons that should be present in each of this orbital. SPDF. The maximum number of electrons in S is 2, the one for P is 6, the one for D is 10, and the one for F is 14. Right? Now, how do we write electronic configuration? Those are part of the things that we'll be mentioning in our next video. And what you are seeing right now on the screen is the limitation to Bohr's atomic model, where it the Stark effect, the Heisenberg uncertainty principle, and it could not explain the spectra obtained from large atom because it can only explain the spectra obtained from hydrogen atom only. So thank you so much for watching, and we have come to the end of this particular session. Thanks so much for watching, and subscribe for more. Thank you.